So welcome back, everyone. For our next talk, we have Darsh Nathawani from LSU. We kind of got a forward pointer for his talk yesterday from Chris, and he's going to talk to us about the Proteus toolkit. Darsh, thanks for being here.
Yeah, thank you. Yeah, so hi, everyone. So I'm working with Chris Keys, who talked about these problems, multi-phase problems with cut-fem that we are interested in for mangroves. So my agenda for this talk is to talk about Proteus Toolkit, which is what we are using to solve these problems. So this is mostly going to be informative talk. So I'm going to talk about what Proteus is, what are the capabilities, and just a tiny demo of how you can get Proteus and run things. And then I have some technical stuff where I'm going to briefly explain how we solve these multi-phase flow problems with a conservative level set. And we were interested in doing some scaling studies to see how we are doing in terms of performance, so I'm going to show that at the end. Okay, so what is Proteus? Proteus is a Python package for rapidly developing computational models and numerical methods. So it's a collection of Python modules and scripts, and it uses C, C++, and Fortran libraries, which are either part of Proteus or either coming from external open source packages. So the design and organization idea of Proteus is to keep two things in mind. So we want to make it easy to solve new model equations with existing numerical methods, and we want to make it easy to solve existing models with the new numerical methods. So using this design philosophy, the way typical Proteus example that you can run is you can have two different Python files that describe, one describes your physics and another describes your numerics, and you use the script to run the code. And I'm going to show that in the next slides. So it makes it much easier to understand the existing code, and it makes it easy to write new examples that you want to do. So just a short demo of how you can get Proteus. So you can go to the GitHub where all these instructions are. So the simplest way to get Proteus is just to use conda and install it. But if you want a developmental installation, you get the Git repo, create the environment where we already have YAML file where all the dependencies are. You provide that to create your environment, and just use pip to install your editable version. But it's slightly different in HPC installation, which is where PETSc is really handy for us. Is you probably want to build all the dependencies from the source, of course, in your environment prefix. So you create this environment and then use PETSc configuration to build most of the dependencies that you need. So you want to make sure, two things I want to mention is that you want to make sure you have parallel HTF5 as your configure arguments. And then you want TEDGen and triangle executables as well. And we have some more additional dependencies. So extensor stack, Chrono, which is open source multiphysics package, and Scorec, which is a C, C++ libraries for unstructured mesh. And you can build this with CMake. And the final piece is you just install MPI for Pi, H5 Pi, and PETSc for Pi using pip. No build isolation, no binary. And finally, you install Proteus. So it's a long process, but it's not difficult. I've built it in 3 different machines, and it works smoothly. Okay, so once you have Proteus, here are all the tests, existing tests are in the tests directory. And the way you run Proteus code is you use the script pa run, which is in your prefix bin directory, and provide your code. So here I have Poisson problem in 3D, and which has two different files. So the first one is _p, which has all the physics in it, and then _n, which is where all the numerics is. So this is the simplest way to just run the code. Additionally, what you can do is you can provide command line arguments. So you can use help to get all the options, but two particular options I want to mention is -c, which you can use to add context options, and -p, where you can add all the PETSc options. So this is how Proteus interacts with PETSc. So Proteus uses all PETSc for all the numerical linear algebra, so vec, mat objects, KSP, preconditioner, and so on. Okay, so what are the capabilities? So we have several different models. So for the multi-phase Navier-Stokes, we have two-phase flow, three-phase flow, two-phase with immersed boundary. We have shallow water equation. We're solving free surface flow with volume of fluid, non-conservative level set, and with conservative level set. We also have multi-body solid dynamics, which uses classes from Chrono. Here is just a list of tests problems that we have. So we have Poisson equation, heat equation, a bunch of advection, diffusion, reaction equation, and so on. So this was a informative part of what Proteus is and what it can do. So to switch to the more technical part, I just want to explain briefly the way this two-phase Navier-Stokes equation is solved. And this is from just the idea from the 2019 paper by Manuel, Dimitri, and Chris. I'm still in the process of understanding how Proteus is implementing this, so it's work in progress for me, but I just want to make sure to explain it. So we have incompressible Navier-Stokes equation with variable material parameters. So density and viscosity are varies because you have two different phases. And you solve level set equation for the interface using the smooth sign distance function, which is just 2 times this regularized Heaviside function -1, just to get the symmetry around the interface. And the way it is solved is explained in the paper is, so the idea is you use operator splitting method. So what you do is first you extrapolate the velocity using the velocity at time level n-1 and time level n. Use that extrapolated velocity to get your level set function, and that allows you to define your density and viscosities with using the regularized Heaviside function. And you can use your material parameters to solve Navier-Stokes equation using projection method, right? And the idea of this projection method was from the paper by Grimond and Salgado. And I don't have description of the projection method, but basically what you do is you extrapolate the pressure the same way as this velocity. You use the pressure and your material parameters to solve the momentum equation for u at time level n+1, and then you solve the Poisson equation to correct the pressure, right? So I'm trying to understand how Proteus is implementing this approach, but since we're already solving Poisson equation for pressure correction, we are interested in looking at some scaling studies using Poisson, because we're going to solve these multi-phase problems using HPC clusters. So we wanted to know how we are or where we are in terms of performance. So we did some simple scaling studies using Poisson equation. So it's a simple Poisson equation in unit domain with non-homogeneous boundary conditions. Some manufactured solution. This is the mesh. So I'm using 60,000 vertices per processor for weak scaling, 120K for strong scaling. And these are the plots that I have. So all these simulations were performed using Louisiana optical network infrastructure supercomputers at LSU. So I'm comparing the Proteus example that I mentioned. Poisson example that I mentioned in Proteus and PETSc. PETSc already has this in SNES tutorials, example 13. So I have a speed up and parallel efficiency data, which is pretty comparable. So currently we only have up to 64 processors. We want to run more, but we are having some, issues with the mesh distribution. So we are trying to figure it out, but so far it's pretty good. And what I want to do next is we are interested in adding dmplex in Proteus to handle meshes so that we can use all the infinite dmplex options from the command line. So but it was a pretty short talk. Right, so that was it. I do have a small announcement flyer. Chris, do you want to do the announcement? Or?
Yep, so I just wanted to let everybody know we are having the SIAM conference on mathematical and computational issues in the geosciences at LSU in October, so October 14th through 17th. I know that's a tricky time for people outside the U.S. to come, and some of us also that are teaching, but there will be a PETSc tutorial there on one of the days. We're currently working on the schedule. Travel grants are still open. Registration is still open, of course. We've technically closed on the program, but I'm sure that we could probably squeeze in a few more talks from folks here if anybody has interest. I have a full list of the planned sessions. They're just not scheduled yet. So again, just wanted to, if you're a geoscientist or you're working on geosciences applications, we'd love to have you come visit. I think we've got a great program, and it'll be a fun place to visit. So again, we're looking forward to having the PETSc tutorial there, and hope to have a lot of sponsorships for particularly student travel grants to come down and do the tutorials and participate in the conference, even if they're not presenting. So thanks.
Thank you.
Yeah.
Okay, thanks to Darsh.
Thanks.
Any questions?
I have a comment and the guys have a question.
Sure.
So can we go back to the splitting? I think you can do that splitting for the Navier-Stokes by doing field split and then doing pre-only and then doing if it's let's see, to get the correction, but I think you can do that just by having a certain solver for both blocks. What that would get you is that even though you were splitting it up and solving in sequence there, you would still get a unified residual valuation at the end. Okay. And what you could do is you could visualize, you could plot the residual and see where the splitting error is, which is sometimes hard to look at if you have them completely separate. And the neat thing you can see, because I did this for a couple of them when I was doing experiments like every possible Stokes solver, what happens. When you plot them, you can see like at the end, you're enforcing incompressibility, but it might not be completely consistent with the velocity field, right? So you can see, does this happen just on the boundary? Does this happen, just a little bit everywhere in the domain? And it's a neat thing because then you could play with some of the parameters to see what what the effect is.
Okay.
And you could do a monolithic solver that's too expensive or something just to compare. So setting it up that way, it does allow you to do the splitting method you want, but you can also do a bunch more things. That's the point of field split, is that you don't break down your problem in the code, you break it down dynamically at runtime, so it enables a larger class of things to be done.
Yeah. I'm not sure how we are using it in Proteus. I do remember talking to Chris about using field split, but
we have a fully implicit. We have the fully implicit formulation.
Oh,
You
okay.
can have some field split preconditioners for it. So we implemented a variation of the pressure convection diffusion splitting. But I've never tried to actually implement the projection scheme with it. So that would be really nice, I think.
We should try and do that, because I think, because then we could say, this is another thing you could do. I hadn't thought of doing it until Darsh explained it, and I'm like, you could do that with field split.
yeah. Cool.
Okay.
So what density ratios are you looking at? Right, because the problem is if you do air water,
Yeah.
you're not solving the Poisson problem. You got a variable coefficient one where the coefficient has a 10 to the 3 order difference. Right, because you're actually solving divergence of 1 divided by density, gradient pressure equals that.
We're doing air water.
Air water,
That paper, the second one that's listed down there, the splitting that we're using from Germano Salgado was derived for density-dependent problems.
Yeah, I'm familiar with that one.
Okay,
Yeah.
all right. So it's true that the Poisson problem that you get out of that is not as simple as the Poisson test that we're using.
Yeah.
I'd be interested to see what scaling and make sure that actually works.
And actually, in the mantle problems that Margaret was doing, the viscosity ratios are like 10 to the 6. And
This is density ratio.
Oh, the density ratio.
Right, because when you're doing pressure projection correction methods like this, you have density times advection, and then you want the divergence to be 0, so you got to have 1 divided by density times the gradient of pressure, take the divergence of that.
Yeah.
Yeah, I don't think we have any of those tests for those density ratios. We did density ratios like that for the droplet thing, but there's no like Poisson stuff where you have because you want the mass matrix in there.
Yeah, what I'm just saying is once you get to that, may not completely match what you're doing with the simple.
Right. Yeah. That's a good point. Right. Anything else?
I got a question for you. The failures that in terms of doing the scalability studies higher to much larger core counts, is it just the Proteus partitioning that's causing it to hang up, or is it also the DMPlex version that's?
No, so I don't have the DMPlex version of the Poisson in Proteus yet. I'm figuring out the boundary conditions, but it's coming. So the message I got from the HPC administrators is, there is a lot of I/O because we were doing this mapping in HDF5 file, right? So they're saying that your problem is, doing a lot of I/O, which is, overloading the machine or something like that. So they cancel the job. I don't know.
An example like PETSc example 13, or have you run it up, or just you haven't tried it yet?
that is working.
Okay.
Yes.
Because I'm doing in 13. I'll tell you what I'm doing, because this is I am just regularly refining in parallel. So we load a tiny thing, or we just generate it, not even load it, and then spread it out and then refine it. So it's totally simple, but it's scalable. If you load it from disk, what can happen is that I/O generally will be like one I/O node for the whole thing or something, and if everyone hits it, like if everyone loads, you can easily just overload the network. We even with some of the rocket stuff, I think as Al here, when we were loading up, we were getting that. As you increase the number of nodes that you use. So For these tests, I tend to just generate simple meshes instead of like going to disk for anything. Of course, if you do something complicated, you don't have a choice.
Yeah. I do want to talk to you about creating this kind of mesh with DMPlex, but we can do it offline.
Yeah.
Yeah. All right. Thank you.
All right, thanks again.